Hello. Welcome to episode -5 of the LearningMeasure.tv podcast. This is a video podcast for the website learningmeasure.com, a training and consulting website. My name is David Archer. I'm the owner of learningmeasure.com and learningmeasure.tv, and this is our first attempt at some sort of podcast. And this first episode is, like I said, -5 is here to try to test out some of the equipment and see what's going to go and give you some idea what we're going to be doing once the podcast is going. I personally have 20 years experience as an engineer. I have a PhD in physics, and this is my baby here. Here's our new set that we just made for this whiteboard. If anybody out there have any good suggestions how I can light this whiteboard in such a way that you can see the whiteboard and see the person in front of it, I'm having trouble with that. Anyway, one of the things that learningmeasure.com does is we have a consultant network that we're trying to build. If you'd be interested in, if you're a consultant and would like to list yourself as part of our network, we plan on interviewing on the podcast people in our networks, give you a chance to advertise what your consulting business does. Next thing that we'll probably have on the podcast on a regular basis, we're probably going to do some measurement-related news. As I should have said earlier, is our podcast is a science and engineering podcast with emphasis on measurement. What we're trying to do is cover things like measurement technology, the underlying theory, maybe the role of modeling and simulation, data processing, maybe automation, anything related to the measurement field. And we also would like to do interviews. If you're a scientist or engineer or technician and are in the Las Vegas area and would like to be interviewed on this podcast, we'd love to have you. The other thing we'd like to do on this podcast is to do product reviews of test equipment. If you're a test equipment vendor and would like to demo your wares on this podcast, we'd love to have you. Also, if you want to advertise or be a sponsor of this podcast, we'd love that as well. We don't know where this is going. This is our first attempt. Like I said, that's kind of what we're doing now. This first section would normally have some news, but we're not going to do that this week because we're just going to try this out. Then there will be a section of the podcast where we cover one topic. We'll do that in this podcast. Hopefully we'll connect them together, and we're going to see how that works. This particular topic, I thought we'd go over this one since it's got emphasis on measurement in our business here. I'd say we talk a little bit about measurement. First thing is, what is a measurement? Well, measurement is basically some sort of numerical, some sort of quantification of some thing that you want to measure. It could be weight, it could be light levels, it could be sound levels, it could be anything. But what a measurement really is a unbroken chains of intercomparisons against agreed upon standards. We're going to talk a little bit about some of the terminology used in measurement. One of the terms used is measurand. You might have heard that word used in measurement. A measurand simply is the quantity you're trying to measure. It could be area or volume or electrical resistance or some other thing of some specific device, or like a particular measurand might be measure the current through a specific resistor, something like that. The other thing that you might come across is the idea of true value. A lot of times we like to think that some measurements we make have what's called a true value. And that would be the value of the measurement if we had perfect measure equipment with no uncertainty and nothing changed. Never, you will never have access to the true value of any measurement. It's just not possible. All measurements do have uncertainty. All measurements do have dispersion. They have, there's drift involved in the quantity you're trying to measure most likely. Even if it was true right now, it won't be true in a millisecond that that's the value that you measured. So true value is something that's totally inaccessible. We might, and I tend to define something called conventional true value in this case, which is the value, the best value you could possibly get for the quantity given the current state of the art, which will change with time. Now we're going to talk about another term, error. Now error is something that if you knew the true value, you could correct for. True error is defined as true value minus the measured value. Okay, so in principle, if you knew the error, you can correct your measurement by adding the negative of the error to your measured value. Sometimes the negative of the error is called the correction. You might sometimes you might get the relative error. The relative error is the error divided by the true value, expressed as a ratio. Sometimes 100 times this is used to represent the relative error in percent. Sometimes the relative error would be measured in parts per million or parts per billion, which is basically 1,000,000 times this and 1,000,000,000 times this. But even though the true value is inaccessible, the conventional true value might be. The best measurement possible may be available, and you might be able to determine an error to correct your measurement. Now, one thing I should say is that no matter what measurement you make, there always will be some uncorrected errors. There's no way to avoid it, because at some point you're measuring some quantity with some sort of test equipment. It has finite accuracy. You don't know from, even if you have the most expensive piece of state-of-the-art test equipment, if you maybe put another order of magnitude of money into developing next level, you might be able to correct some of the errors that you missed. But you will never, ever eliminate all errors in a measurement. It's just not possible. Okay, that being said, there's another concept called uncertainty. Uncertainty is defined as the likely dispersion in the measurand. In other words, how far off the measurement is likely to be from the true value. Uncertainties are not things that you can correct for. They're not errors. Uncertainties, all measurement has uncertainty. You cannot make a measurement without uncertainty. In some cases, for instance, if you've heard about something like the Heisenberg uncertainty principle, you can measure where something is to as accurate as you want, but then you have no idea of its momentum. There's some uncertainty law there. So there are fundamental limits of how well you can know something, even if you had perfect test equipment, which is not possible. So there always will be uncertainty in measurement. A lot of measurement, most of measurement, involves determining the uncertainty. In fact, if you don't have an estimate for your uncertainty, you haven't made a measurement. You know, if I told you I measured the length of some bar to be 1.05 meters, and that doesn't tell me anything, what if it was plus or minus a light year? Okay, you don't know. If you can't say that, sometimes that would be implied. If you say 1.05, you'd think it would be at least to maybe 0.01 meter, but you don't know that without an uncertainty statement. You cannot make a measurement without an uncertainty estimate. If you don't know what your uncertainty is, you haven't made a measurement, because you don't know how far your measurement could be from the value you got. Okay. Why would you measure? Well, one of the things you would measure for is maybe to verify compliance to a specification. Is the part intolerance? If your Cal Lab is the piece of test equipment intolerance, did you get what you pay for? If you wanted to get 5 pounds of peas, did you get 5 pounds of peas? That's all compliance to a specification. One reason you might measure is to verify physical law. You have some theory of how the universe works. The only way that you can rule it out is by measurements. So, which is one of the problems with science, right? You can never actually prove you're right, you can only prove you're wrong. But if you make measurements and all the measurements are consistent with the theory you've developed, it's highly suggestive that your theory is probably correct. But all science proceeds by making measurements and comparing against theory. And you have to have theory in order to even make a measurement. Safety is one reason you might make a measurement. Some of that might be verifying specifications, but might not be. For instance, if the temperature is too hot in a certain environment, you may have an explosion risk. That's a measurement that you might have to make for safety reasons, to diagnose problems. Your doctor might take your blood pressure, do blood tests, measure your temperature. Your auto mechanic will do something to measure what your car is doing in order to diagnose what might be wrong with your car. And then the last thing I wanted to talk about, this is being a short one, is what happens in every measurement. First, you have to have you must make a prediction. You have to predict what the value you're going to measure is. This is always important. You have to understand the theory. You have to understand what uncertainties you expect of your measurement. If the thing if you're trying to measure a spec to a millimeter and all you have is something that can measure to a centimeter, you have a problem. So you have to know in advance what you expect of the measurement in order to design the test setup. Prediction has to come first. Then you make the measurement. Once you make the measurement, what do? You compare. Compare the result with the you compare the result with your prediction. Sometimes you may go back to your prediction and go through a cycle. If something's wrong, you may have to do some action. Revise your theory, throw the part out, rework the part, adjust the piece of test equipment, prescribe medication, some action that comes out of comparing your prediction and your measurement, which oftentimes lead you back to here. Sometimes would lead you back to here. You perform the action, give the person an aspirin. An hour later, remeasure their temperature. So this is the measurement cycle. This podcast hopefully will cover something in each of those 4 blocks with time. One more thing. What we had alluded to. We were talking about underlying theory. For every measurement, there's something called the measurement equation. And I'll give you an example of one. You want to measure the area of a rectangle. The measure end is the area of the rectangle. Well, we could measure the length and the width. And our measurement equation would be this. Area is equal to length times width. Okay, this is the measurement equation for this area of this rectangle. Problem is, if you don't know in advance what kind of accuracy you expect, this may not be adequate. And what you may find out, in a real measurement situation, your measurement equation may not have enough terms. If you want this plus or minus, let's say, a square foot, maybe just measuring this and measuring this with a ruler and using that's perfectly adequate. But if you wanted to measure this to plus or minus a square millimeter, obviously that's wrong because, first of all, the sides aren't straight. These aren't really right angles. So there would be terms that you would have to do something, you'd have to have a different measurement equation to get the actual area inside this box. The other problem you might have is, well, there are other terms in here that weren't collected. The temperature might cause this whiteboard to expand and contract. This is backed in wood, so the humidity might cause this thing to expand and contract. So the humidity, temperature, and other things were things that might be added into this measurement equation. An example where the theory, underlying theory, may be wrong for the measurement you're making. Every measurement equation that you do put together, you will have terms missing. That's part of your uncertainty. How you analyze that is tough. But we always will have something omitted from your measurement equation. Anyway, that's where we're at today. That will be it for this episode. We don't know where this is going. We hope it'll go, but in the next few weeks we'll have some other people on that are also working behind the scenes. But right now, this particular episode is to work things out with the camera, the whiteboard, the RSS feeds, all that sort of thing. What we'd like now is from you guys suggestions. If you're interested in making a suggestion for what we should cover on this podcast, send email to suggestions@learningmeasure.tv. If you're a vendor wanting to be on the show, or if you wanted to give a press release on any new test equipment or anything like that, and you want to put us to put it on the show, email us at vendors@learningmeasure.tv or learningmeasure.com. Finally, if you want to advertise on here, also email us at vendors@learningmeasure.tv. That's it for now. Who knows where this is going? The next one will probably be better than this one. Let us know what you have in mind. Thanks. Goodbye.